Okay, so we did not talk about much about metallic yesterday. It is an intramolecular force, and then we're going to look at the rest of the bonding types. So metallic bonding, I wrote intramolecular here just to reemphasize it. So it is transition metals only, and what happens is you have this random, not ordered, so sometimes it's called delocalized electrons. So really, like I said, if somebody makes you draw a Bohr-Rutherford diagram for a transition metal, then that's really sort of stretching the limits of those diagrams, okay? Valence electrons are loosely held. They are not found in flat orbits, allowing them to provide a path for electricity. So copper can be used to make wire because it will conduct electricity in the solid form. You might even have copper pots in your house, so it'll conduct heat, all because the electrons can move around. So the next slide has a picture, and it tries to show this in a unfortunate 2D way. So what it is it's kind of like, we call this a sea of electrons. So the red circles are meant to represent the metal nucleus. So when we talk about or use the word metal nucleus, so it's the same sort of nucleus as any kind of element, protons and neutrons. But then we also consider the inner electrons, like not the valence, to be part of that nucleus. So they're tightly held. Those ones don't move around. They'd be more like what you would expect, as the same as another atom. But then the valence electrons are delocalized, or it's a loose sea of electrons. You can even use the word oscillate, so they kind of move back and forth against each other. They are not stuck in the Bohr orbits at all. And you may have heard the word local before, like maybe you've had a tooth pulled and you get what's called local anesthesia. So like they won't put you out totally. They'll put like just a specific spot of freezing. So it's like a specific spot that's local. So then D-local means like no specific spot. You can even think of it that way. Okay, so that's really all we're going to say for that. Metallic bonding, transition metals. So when you get to the intermolecular forces, it is between molecules, which was a definition we wrote yesterday. And we talked about only for covalent or molecular compounds. Again, because ionic is cation, anion, cation, anion, cation, anion. Very boring, very rigid structure, which you'll get to see today. So these are formed and broken during physical changes. So what we're going to do more next year, again, we're going to extend this even further, and we're going to talk about the strength of the force in relation to the energy. So at the end of grade 12, or by the end of grade 12, you'll be able to look at molecules, decide about their structure and what kind of intermolecular forces there are, and say whether they have high or low melting and boiling points. That's one of the expectations for that. So here, what we're going to do is look at when these forces form, okay? And we're going to use, again, we're just going to build on what we did yesterday. Do the math first, figure out what kind of bond, and then figure this out, okay? So we have, when you have a stronger force, then it's harder to get it apart. So that's an underlying theme, right? The more attraction, the harder it is to get apart. It's true with molecules as well. So we're going to go in order of strength. So the strongest force of attraction is called hydrogen bonding. And we don't even, the rest of them we call forces. We call this one a bond because it is so close to being ionic. And hydrogen bonding, it is vital essentially for life on Earth. So many properties of water exist because it can hydrogen bond between its molecules. Again, if you're into biology, you'll talk about hydrogen bonding in terms of DNA structure and what kind of biochemical molecules inside of us are attracted to each other. So the reason the bond is almost ionic, almost on the edge, is because you have to have hydrogen, obviously, it's a hydrogen bond, but then you have to have nitrogen, oxygen, or fluorine. That's it. So these elements are so electronegative that they're so greedy for electrons, they almost steal them from the hydrogen, fully like transferring, okay? So sometimes people, again, if you're into tricks to remember things, people will say FON or NOF. You certainly don't need to. And actually, it follows the pattern. So the trend in electronegativity increases towards fluorine, which you could see in your chart, but then they're right beside each other. Fluorine, oxygen, nitrogen. And of course, hydrogen, okay? So these three bonds, HF, HO, and HN, are very polar. So one end of the molecule is slightly negative, the other is slightly positive, and in chemistry, opposites attract. So the charge difference means these molecules are attracted to each other. And again, it's so close to being a full ionic charge, the attraction is very high. So things like, if you've ever, in grade 9 science, we do static electricity, and we talk about, transferring charges, but when you rub something, like say you rub a balloon on your head, and then you make a stream of water, and it bends towards the balloon, you might even use like gross rabbit fur to charge a comb, and do you remember that? And they talk about it in terms of just charges, right? Static electricity, charging by induction or whatever, but really what's happening is, yes, the water is attracted, but the reason it's not like splashing off onto the comb or the balloon or whatever, the reason it's bending a stream is because the water molecules are so attracted to each other. So they're making this like hydrogen bond of water molecules, which is then attracted to the balloon. So there's actually two things going on there. Or if you think about trees. Yes, it rains for the leaves at the top to get water, but trees also have roots. Why do they have roots? So what happens is there's these tubes inside plants called xylem. So again, if you're into biology, you'll talk about those. And the water molecules from the ground form hydrogen bonds, like a little chain, so that the roots can provide water when there's not a lot of rain to the top of the trees. The reason that ice floats when it's frozen, when it becomes a solid, it makes hydrogen bonds. The hydrogen bonds are so regular, they make a characteristic space. You could actually measure the distance between the water molecules, and it creates pockets where there's nothing, which makes it lighter, and it floats. So you can imagine if water didn't do that, or ice didn't do that, we have lakes. They would freeze, the ice sunk, everything in that lake every single winter would be crushed by these sheets of ice, right? Obviously not good for life. So there's a lot of things in nature that exist because of these hydrogen bonds. So what we do when we draw these structures, so again, in grade 12, it's more important to be able to draw them. You guys mostly just kind of have to interpret them, okay? So this is a Lewis structure for water, right? Except we haven't shown the dots. We're trying to simplify it. If that bothers you, let's draw them in. Because technically, oxygen has 6, right? So there would be so when we do Lewis, like this, whether you do dots or lines, doesn't matter, that is flat, right? We're trying to show a molecule on a flat piece of paper. But one of the things we're going to do next year is draw 3D. So the reason it's drawn like this, where the pairs of electrons are at the top, and then these two hydrogens are kind of angled at the bottom, is it's called angular, it's shape. So what happens is those pairs of electrons are so repulsive, their negative charge is so great that it actually repels and pushes all the atoms away from it. So really, in a water molecule, the oxygen has the lone pairs, so its slightly negative side would be up here, and then the hydrogens at the bottom would be the slightly positive. For you guys, this is more than enough. You could draw it however you want. You could draw it like this. You could draw them on the other side. Okay, you don't have to worry about 3D. But if you're wondering why that looks like that, that's why. Okay? So then the other thing you have to do, so let's say, so again, I'm not a trickster. Part A, do the math. Okay? So we'll do, find the delta E and G. So O minus H, 3.44 minus 2.2. And remember, you don't need to memorize those values. They are on the periodic table. Okay? I chose to do O first because I didn't want to make it negative, but it doesn't matter. So then you would say, okay, 1.24, that is going to be polar covalent. I just used the chart down here. All right, also don't need to memorize, just have to know how to use it. But now, when you have polar, then you want to go check your structure, okay? Okay, so polar covalent, that means unequal sharing, so I have to label it slightly positive and slightly negative. So that's why I wrote it like this, like O minus H, to emphasize this is oxygen and this is hydrogen. So oxygen has a larger electronegativity value. That means more electron greedy, so it's going to be slightly negative. So every oxygen you can go and label slightly negative. And then the hydrogens would be slightly positive. So this picture is as simple as possible. So obviously there's some, like you could draw even more water molecules, you get this whole network, but we're just trying to keep it simple here. So yes, sorry. No, you could put it any, as long as I can tell you're saying oxygen slightly negative, hydrogen slightly positive, that's fine. You could write it up here. Okay, good question. So now when you draw them in, you can see, oh, slightly positive, attract to slightly negative, slightly positive, attract to slightly negative, right? Opposites attract. So in order to show the difference between intramolecular and intermolecular, we use solid lines and dotted lines. And so the solid lines, like this bond here, this is the polar covalent, right? So that's intramolecular between atoms, which are always stronger than inter, okay? So how do we show that strength? We use a solid line. This says the dotted lines are used to show where hydrogen bonds form. You could use dotted lines for any of the intermolecular forces if you had to draw the picture because they're a little bit weaker. So how do we show they're weaker? Like broken lines, right? Dashes. You could do, some people draw them like circles. It doesn't really matter. They just have to be broken, not solid, okay? So if you want to label that here, so I'll pick green. And then it does say here the dotted lines are used to show where hydrogen bonds form. So you could put intermolecular there if you want. Because any of the intermolecular forces you could show using broken lines, and any of the intramolecular you could show using solid lines. This is a difficult picture to draw, okay? So what you should focus on in grade 9 is, grade 11, sorry, the Lewis structure for sure, doing the math for sure, remembering that polar covalent, you have to label the slightly positive, slightly negative for sure. Do you have to draw this network thing like this? No, okay? I think we'll save that for next year. Could you recognize it like in a multiple choice question maybe, but that would be the most. Okay, so when the next type of intermolecular force are van der Waals. Now, to be honest, or if you're Dutch, van der Waals, but we usually we separate them even further. So hydrogen bonding, like I said, it is the strongest, and it's so close to being ionic because of the electronegative elements. But there are other polar covalent substances that don't have hydrogen or nitrogen, oxygen, and fluorine. So there has to be other forces involved. And then we're going to talk about London dispersion. Sometimes you could just shorten it to dispersion. Sometimes you could just shorten it to London. Usually, I think we shorten it to dispersion. Okay, even in grade 12 too, or your biology teacher as well. So these ones, so hydrogen bonding is a special class. Hydrogen, nitrogen, oxygen, fluorine. Dipole will be And then by default, we only have one type of covalent substance left. So this would be, sorry, I run out of room there, non-polar. So for grade 11, you do the math, figure out what kind. If it's non-polar, your job is done. London dispersion, easy. Polar covalent, you have a choice, okay? So that's what we're gonna do. We'll go through we'll go through the types, and then the last few slides are gonna be trying to summarize, like what happens if, okay? So let's look at these two definitions. So dipole, and hopefully kind of you can see the clue here is in the name, the force of attraction between polar molecules. And if you want to write in that don't hydrogen bond, so when you get polar, you do have a choice, okay? So let's do hydrogen and chlorine, okay? So we'll go through all the steps. Okay, so sometimes it helps with a picture. Let's draw a picture. So we have hydrogen and chlorine. Polar means you use the slightlies. Oh, if you're a bubble person, that's fine too. It works. So, again, this would be an incredibly difficult question, but if you had to draw what was going to be next, then we could add in another hydrogen here to be connected to this. But you do have to decide what kind of force would be between them. So when it's polar covalent, you check. Can it hydrogen bond? Good writing there. Can it hydrogen bond? It has H. Yes. Does it have NOF? No, it has chlorine. Okay, so even though it has hydrogen, it can't just be hydrogen. You have to have both. Okay, so no. So once you do that, once you eliminate that choice, then it has to be dipole-dipole. So, I mean, you could certainly write this, but if you had to give a reason, you could literally say dipole-dipole, can't hydrogen bond but polar, and that would be good enough. Even if you just wrote dipole, you don't have to, we even, again, chemists are lazy. You don't have to write dipole-dipole. You could just write dipole. That would be good enough. So if we were going to draw one in, okay, so let's draw another one. So again, this is slightly negative. So close to the negative would be the positive side. And then somehow between them, show a broken line. Do you like a dotted broken line? Sure. Do you want it to look like the other one? Sure. Make it dashes, whatever. So you just want to make sure it's not solid. Intermolecular forces are weaker, so we use dash lines. Okay, and then the last kind is London dispersion. So the London part comes from naming it after the person to first describe them. The dispersion part is a better term, I think, because it describes what's happening. So when you have a nonpolar molecule, so then when you have a nonpolar molecule, you would think, oh, that's equal sharing. They're not going to influence each other. But there's a lot in the world that has charge. So if you ever have, including us, if you've ever like walked by a radio, like an old school radio, and you change the reception, some people will complain about not being able to wear like an old school analog watch because your, forces or whatever change the time. And so we are full of magnetism. The earth is moving, it's full of magnetism. Electrons themselves are vibrating and turning. So what can happen is, even in a nonpolar molecule, the dispersion of electrons can change. So if it's, let's say, left and right side, I'm a molecule, and all of a sudden, maybe somebody has put a magnet near me. We'll be more in depth next year, but you could even have like an ion influence, something with a charge influence me. But so then I change my dispersion. So now my electrons are all vibrating on my left. That means that for an instant, if the substance is close to me, then my side would be slightly negative. If I then went to molecule Logan and I was close to him, then I would influence him. I'm slightly negative, he would change his dispersion to be slightly positive. And then slightly negative, he would influence molecule Abby, and you would get this network of molecules. As soon as I moved away, Logan would go back to normal, his dispersion would change, so would Abby, right? So it's like this constant vibration and movement of electrons that can change the dispersion. So yes, London is a person, but the dispersion part is a little bit more descriptive of actually what's happening, okay? So it has to be instantaneous. It is a very slight attraction. These are not strong forces compared to dipole or hydrogen bonding. And it says it induces a dipole in another molecule. It just talks about molecules. I would even put in specifically to help yourselves, nonpolar. So if you want to use a short form, so when you get to nonpolar, London dispersion, done. It's the only choice. Because Nonpolar has no slightly positive, no slightly negative. We would have called that equal. So it has to be an instantaneous dipole, only exists for a moment. They have to be very close together, like in a liquid. And then next year, we'll look more into this. The more electrons, the more protons you have. So we're going to start to build molecules that aren't just HCl or HOH, or HO. We're going to make these big molecules. And you'll probably talk about this in biology as well, because our bodies are full of big molecules. And what happens is it makes the forces stronger. The more there is, the more they can attract. Okay, so you guys have a blank, right? Beauty. So what do you have to do? Okay, so you're going to do delta E and G first. Delta E and G to determine intramolecular, and there's three choices. Ionic, you might think, Ms. Todd, what about metallic? It's intramolecular. Why isn't that part of it? A couple of reasons. First of all, it can only be transition metals, so they're a little bit easier to pick out. Second of all, their transition metals are common and we exploit their uses all the time, but making them a bond and making them a compound is not as common. Okay, so you can get more variety with ionic and polar and nonpolar. So we focus on those. Okay, so ionic, so do delta E and G to determine the intramolecular, and now you have a choice for intermolecular. Ionic has none, right? Rigid, you can even rate boring, plus minus structure. So nothing funky can happen with those. So if you want, you could even put a definition up here if you still have space. Like this is transferring electrons. This is unequal sharing. Equal sharing. If you want to emphasize it for yourself, okay? So the fact that ionic transfers, plus minus, plus minus, plus minus, boring. So then nonpolar is, there's only one choice. So that's easy. And when, let's say it asks you to like choose the force and then write reasons, you could literally put Lennon dispersion because nonpolar, and that's good enough, okay? That's as far as we're going to go this year. So then polar covalent, which is unequal sharing, this is where you have choice. So I recommend you check for hydrogen bonding first. Actually, I want your shirt on. So hydrogen bonding has to have H and NO or F, nitrogen, oxygen, fluorine. If this doesn't work out, then it's dipole-dipole. Okay, so let's do, and again, I'm not going to make you fill in a chart like this. So if you don't like flow charts, it's not the way you like to study, that's fine, okay? You are going to have to do questions like this one. So we're going to, part A, use the ENG to determine if it's ionic, polar, or nonpolar covalent. We're going to draw the Lewis structure and determine if there are any intermolecular forces. So because we did a bunch of ionic compound Lewis structures yesterday, the ionic compounds don't have any intermolecular forces. The three examples are basically going to be one polar, one nonpolar, and one hydrogen bond, okay? But again, I'm not a trickster. I'm going to show you every time. Part A, do the math. Part B, draw the structure. Part C, now do the intermolecular force. Okay, so we have the first one's chlorine and chlorine. Chlorine is a diatomic molecule. So again, if I was ruthless, I could just say chlorine and you would have to remember that it's diatomic. Okay, so use your table. Chlorine minus chlorine, 3.16 minus 3.16 is 0, therefore nonpolar. Whether you do a nonpolar or polar dipole or hydrogen bond, it doesn't really matter for the Lewis structure, except the polar ones you have to add in the partial charges. So but the basic Lewis structure between the atoms is the same. So whether you like bubbles or you like lines, it doesn't matter, you can choose. So chlorine is a halogen. It has 7 valence electrons. Again, I'm gonna cheat because I want my picture to be pretty, so I'm gonna draw it so it can be connected to the other one, but it doesn't matter. Either one of those is correct. You should be able to check and count that the maximum is 8 or maybe 2. If it's hydrogen, 2, 4, 6, 8, 2, 4, 6, 8. So remember, the bond is sharing. It counts for both. If it's nonpolar covalent, do I do the slightlys? No. So now C, intermolecular. So all you have to do, okay, it's nonpolar covalent. What's that going to be? London dispersion, okay? And like I said, if you just wrote London, that'd be fine. If you just wrote dispersion, that'd be fine. Okay? So then we'll do NH3. Sort of a double-edged sword. Sometimes students, like, I'll give a question and it will just say nitrogen and hydrogen, and you kind of have to figure out how many bonds there needs to be, like how many hydrogens, which is, it seems tougher when you do the Lewis structure, but then sometimes when you do this, students will want to multiply the 2.2 by 3, and you're not doing that, okay? It's just straight up that one element minus the other element, okay? So when you get, if you get a question and it has the formula like that, just be careful. It's not like, you know, like math where it would be like n plus 3h equals, like we're not doing algebra here, okay? Just do one of each, subtract, all right? And then, so now we have polar covalent, but really the basic Lewis structure is still the same. Just when it's polar, we got to go at the end and put the slightly positive, slightly negatives. I know that I put them in a different color. If color's not your thing, you don't have to do that, okay? So I'm just trying to emphasize it. I chose nitrogen as an example on purpose because even in grade 12, sometimes students will forget how many it has, how many valence electrons, because you automatically think nitrogen has a charge of -3, which is fine, but that comes from gaining 3 because it has 5, okay? So count the columns, 1, 2, 3, 4, 5, and then do the never eat shredded wheat thing, okay? It does, again, it doesn't really matter where you have the 3 bonds. Yes, the 2 left over are important. They have to be on that picture, okay? So then because it's polar, we need to add the slightlies. So whichever one is more electronegative. So the way I've written this here, I can tell that it's nitrogen. But you could, it's not like, you know, you have a time limit with the chart. You could go back and look. It's no big deal. And one of the advantages to the quad the whole day, after lunch, you can start your test and then it's not like the bell's going to go and you have to stop, right? So take your time, don't rush. now it's polar, we have a choice. So, can it hydrogen bond? Does it have H and one of NOF? It sure does, okay? There's a variety. If you prefer a little bit longer explanations, you know, it has a hydrogen and nitrogen, which is a part of NOF, whatever makes the most sense to you. But this concise answer I would accept, okay? And then the last one, again, I kind of chose on purpose, okay? So the last one is maybe one where it's unique a little bit. You might want to make bubbles. It might help you see where the bonds have to go, but maybe not. Maybe you're good at this. Again, it's one of those things where it's like, you know, like balancing last year. It seems like a foreign language, and then all of a sudden it's like your brain can just see it, you know? I feel like that happens with this. Okay, so CO2, so do the math. Again, we need, you're just doing 1C minus 1O, or O minus C, it doesn't matter. Okay, so when you draw the Lewis structure, carbon's one of those weird ones that has 4. Oxygen has 6. And it doesn't really matter where you draw it. You could draw it on the left, you could draw it on the right, whatever makes sense to you. I know it says CO2, but I'm going to show you how it works, okay? It says CO2, we already know we need 2, but I'm just going to draw 1 for a second. So this is where I think sometimes bubbles can help, okay? So carbon, again, is in that weird column. It's got 4 valence electrons, and often when you're first talking about what's the charge, like in grade 9 and 10, students will say, well, is it plus 4, is it minus 4? P.S. It's neither, right? It's going to share, okay? So that's why carbon usually just shows up in covalent substances, covalent bonds. There's one very weird substance called calcium carbide. If you are a welder, then that's one of the substances they use like that will create acetylene, like acetylene torches. You can do it with a reaction. You can actually put calcium carbide in a balloon and with water and make a tiny hole and make an acetylene torch in it. Back in the day when they used to let us buy it, we used to do that in my grade 12 class, but now they won't for obvious reasons. Sometimes a balloon would explode and the kid would be like covered in this like goo. It was awesome. But we don't do that anymore. Sorry. But I bet you could Google how to make an acetylene torch and with a balloon, and you could watch a video. I hope, because they won't even let us buy it. I hope that they don't let you buy calcium carbide, but one of those things where you like put it in your Amazon cart and the FBI shows up at your house. Why are you buying this? But anyway. let's make some bubbles, okay? So I drew it on purpose again like this. I drew the lone electrons near the carbon. So I'm going to make bonds. Carbon needs, it has 4 that are empty. So what does it do? Okay, bonds here. I like this one. I like neatness. I'm going to make my picture neat, okay? Now on the other side, we still need 2, and that's why it's CO2. So you get a double bond, okay? So this is like, you know, again, this would be ruthlessly tricky. Why do we have to do, I would not make you try to figure that out on a test. So oxygen is slightly negative, carbon is slightly positive. So intermolecular, it's polar covalent, okay? Is there hydrogen in CO2? No, so it can't hydrogen bond. So this one's actually a little bit easy in terms of that, like there's no hydrogen, not like HCl where there was hydrogen, so then you had to remember the other list. This one, no hydrogen bonding, so then it's going to be dipole-dipole. Okay. So let's just do, again, you know, you can decide how you want to study. This is sort of a unique, this one and a little bit of the next one is unit is sort of unique in that there are a lot of terms and theory. You'll find that much of grade 12 and the rest of grade 11 is mostly like problems in the sense, you know, can you figure it out, which often students like better. So this sheet should be in your booklet, yes? Okay, so we're going to try to make this as bare bones as possible, okay? So intramolecular, if you want to remind yourself, it's between atoms. ANA, if you are so inclined to have a little trick. Ionic has metal and a non-metal. Covalent is non-metal. Ionic electrons are transferred. Covalent are shared. Now, sometimes with metallic, I don't even write anything, but you could put here valence are delocalized. You could put loosely held, you could put free, if that makes more sense to you. So today what your lab is going to do is going to test some physical properties of ionic versus covalent. So, does ionic compounds, do they dissociate in water? Yes. And covalent, no. Just cross that one out. So if they dissociate in water, we haven't talked a lot yet about solubility. However, one of the things that you should have talked about in elementary school, or maybe logically you would know, you can think about like table salt. Can you get a little bit of table salt to dissolve in water? Maybe your mom, when you're sick, your throat's sore, your caregiver makes you gargle salt water. It's like, oh, disgusting. So you can think of this today as solubility. Does it dissolve? So the fact that it dissociates in water means that yes, it dissolves. Okay. Is an electrolyte formed? We talked, that was in the definition of that was in yesterday's note. So today we're going to see it conduct. Does it conduct? Yes. Covalent compounds do not. When you have a metallic bond, the solid actually conducts. It doesn't have to be a solution. So if you want to not have to go look up the definition for electrolyte, you could even write here that this is a solution. The definition is in yesterday's note, like it's in there. Or if you're a textbook reader, it'll be like one of the, they make black and then they have like in the margins the black definition. It'll be in there. Oh, here, never mind. Solution conducts. There you go. Yes. No. Not a thing. Transistor metals are ugly. They're colorful. They're heavy and nasty to ecosystems. So we don't really make solutions. So an example, you can pick whatever you want. Everybody knows or loves table salt, sodium chloride, but you could pick whatever you want. Covalent, let's do the ones you know, okay? So a common nonpolar one is methane. So any kind of gas, so even if you live in the city, you're probably using natural gas, which is methane. If you're in the country, you might use propane or oil, all of that, nonpolar. Same thing. And then let's put water, the most famous polar covalent molecule. And then probably the most common one you've experienced is copper and zinc. Not that we have pennies anymore, but probably in your lifetime you've seen a penny. A penny is not pure copper anymore, it's too expensive. And two, it'll tarnish easily. So it's actually an alloy with copper and zinc. Okay, then intermolecular between molecules. This is the weakest. I know there's a big chart here, but I think we should keep it as simple as possible, okay? So we'll say London dispersion, nonpolar. So London dispersion, it's weak, nonpolar. Dipole, dipole, polar, but no hydrogen bond. So it's right in the middle. And then hydrogen's the strongest, has to have hydrogen and extremely electronegative elements. Nitrogen, oxygen, fluorine. Okay?